Imagine you're looking up at the night sky. Those distant stars and galaxies aren't just sitting still, they're moving away from us. And not just moving, but speeding up. It's like the entire universe is inflating like a balloon, faster and faster. But what's causing this cosmic acceleration? It's not gravity pulling things together, it's something pushing them apart. Something invisible, mysterious, and incredibly powerful. Welcome to the enigma of dark energy, the force that makes up about 68% of our universe, yet we have no idea what it really is. In this video, we'll dive deep into its discovery, the leading theories, the evidence, the unanswered questions, and what scientists are doing to crack this puzzle. Buckle up, we're going on a journey to the edge of the cosmos. Our story begins in the late 1990s, when astronomers thought they had the universe figured out. According to Einstein's general relativity, gravity should be slowing down the universe's expansion, which started with the Big Bang, about 13.8 billion years ago. Picture it like throwing a ball up in the air. It slows down as gravity pulls it back. Scientists expected the same for the cosmos, expansion decelerating over time. But in 1998, two independent teams of astronomers, led by Saul Perlmutter and Brian Schmidt, shattered that idea. They were studying Type A1 supernovae, exploding stars that shine with a consistent brightness, making them perfect standard candles for measuring cosmic distances. By observing how dim these explosions appeared and how their light was redshifted, stretched by the expanding universe, they calculated the distances and speeds of distant galaxies. What they found was shocking. These supernovae were farther away than they should be if the universe was slowing down. Instead, the expansion was accelerating. It was like the ball you threw up suddenly started flying faster into the sky. This discovery earned them the Nobel Prize in Physics in 2011, and it introduced the world to dark energy, a repulsive force counteracting gravity on the largest scales. This acceleration didn't start right away. For the first 9 billion years or so after the Big Bang, gravity from matter dominated, slowing things down. But around 5 billion years ago, dark energy took over, and the speed-up began. Today, dark energy dominates, making up roughly 68% of the universe's total energy content. Dark matter is about 27%, and the stuff we know, atoms, stars, planets, is a mere 5%. We're living in a universe mostly made of things we can't see or understand. So what exactly is dark energy? Well, that's the billion-dollar question. Or should I say the multi-billion light-year question. It's not dark because it's shadowy, it's dark because it's invisible to our telescopes and doesn't interact with light or matter in ways we can detect directly. We only know it's there because of its gravitational effects, or rather its anti-gravitational effects. Dark energy permeates all of space, like an invisible fog that's everywhere, even in the vacuum between stars. Unlike matter, which clumps together, dark energy is uniform and doesn't dilute as the universe expands. In fact, as space grows, more dark energy appears, fueling even faster expansion. It's a self-reinforcing cycle. Think of it like this: gravity pulls things together, like a rubber band contracting. Dark energy is like stretching that rubber band outward with an ever-increasing force. The result? Galaxies are receding from each other at accelerating speeds. If you were on a distant galaxy looking back at the Milky Way, we'd appear to be speeding away from you too. It's not that we're at the center. Expansion happens everywhere. But here's the kicker. Dark energy isn't just some sci-fi concept. It's baked into our best model of the universe, called Lambda CDM, where lambda, L, represents this mysterious component. Scientists have several ideas about what dark energy could be, but none are proven. Let's break them down. First up, the cosmological constant. This was Einstein's brainchild. Back in 1917, he added a constant term to his equations of general relativity to make the universe static, neither expanding nor contracting. He later called it his biggest blunder when Hubble discovered expansion. But ironically, this constant might be dark energy. It's like an inherent energy of empty space, a vacuum energy that's constant everywhere and always. The Lambda CDM model uses this idea, and it fits observations beautifully, from supernovae to the cosmic microwave background. But there's a huge problem. Quantum field theory predicts this vacuum energy should be enormous, like 10 to the 120 times larger than what we observe. That's a 1 followed by 120 zeros, the biggest mismatch in physics history. It's called the cosmological constant problem, and it suggests we don't fully understand quantum mechanics or gravity. Next, quintessence. This theory says dark energy isn't constant, it's a dynamic scalar field, like an invisible energy fluid that changes over time and space. Named after the fifth essence in ancient philosophy, quintessence could evolve, maybe even weakening or strengthening in the future. What makes it appealing? It allows for testable differences from a constant. Scientists measure dark energy's equation of state, a ratio called W, pressure over energy density. For a cosmological constant, W is exactly -1. Quintessence might deviate slightly. An observation so far showed W is close to -1, but we're checking for changes. Then there's modified gravity. Maybe dark energy isn't energy at all. Perhaps our theory of gravity needs tweaking on cosmic scales. Ideas like FR gravity or brane world models, where our universe is a brain in higher dimensions, could mimic acceleration without new stuff. But these struggle to match all data, like galaxy clustering. And for the wildcards, phantom energy, where W is less than -1, leading to a big rip, the universe tearing itself apart, galaxies first, then atoms. It's possible, but speculative. Other ideas tie dark energy to quantum gravity or multiverses, but they're even more theoretical. No matter, dark energy challenges our fundamental physics. How do we know dark energy is real? It's not just one experiment, multiple lines of evidence converge. Besides those type A1 supernovae, there's the cosmic microwave background, the CMB, the afterglow of the Big Bang mapped by satellites like Planck. It shows a flat universe, which requires dark energy to balance the energy budget. Baryon acoustic oscillations are like cosmic sound waves frozen in galaxy distributions, revealing expansion history. Large-scale structures, like galaxy clusters, match a dark energy-dominated model. All these independent data sets point to the same thing: acceleration driven by something like dark energy. Despite the evidence, dark energy is riddled with mysteries. Is it truly constant, or does it change? Why the tiny vacuum energy value? What about data tensions, like differing Hubble constant measurements from Hubble telescope and DES surveys? These Hubble tensions hint at new physics or errors. The fate of the universe hangs in the balance: eternal acceleration, a big rip, or something else. And philosophically, why is dark energy tuned just right for life? Too much and stars never form. Too little and collapse happens early. Scientists aren't giving up. Missions like ESA's Euclid, launched in 2023, are mapping galaxies with weak lensing to probe dark energy. NASA's Nancy Grace Roman telescope, launching in 2027, will hunt more supernovae. Ground-based DESI is surveying millions of galaxies for precise expansion maps. Theoretically, we're exploring dark energy-dark matter interactions or quantum gravity links. Unraveling this could revolutionize physics, new forces, dimensions, or a unified theory. Dark energy is the ultimate cosmic riddle, an invisible force shaping our universe's destiny, yet eluding our grasp. From its 1998 discovery to today's cutting-edge hunts, it reminds us how much we don't know. But that's the thrill of science, turning mysteries into understanding. What do you think dark energy is? Drop your theories in the comments. If you enjoyed this deep dive, like, share, and subscribe for more explainer videos. Until next time, keep looking up.